Did you ever want to travel the farthest away you could from home? Well, that's basically saying that you want to travel the diameter of the Earth, 12,700 kilometers. That's only if we had a tunnel through the center of the Earth. To get from South Pole to North Pole by plane, that would take 20,036 kilometers, or approximately 25 hours. It's true that the fastest point from A to B is a straight line, but that's only on a flat plane. This is why you can draw a triangle with 390-degree angles on a sphere, making a curved line shorter than a straight one. Any geometry student would tell you that it is impossible on a flat surface. But let's say we did have a tunnel that starts at the North Pole and ends at the South Pole, leaving the questions: what is the displacement? What is the velocity? And what is the acceleration? Well, the displacement is the diameter of the Earth, 12,700 kilometers, and the acceleration is gravity, 9.8 meters per second squared. But this number will get progressively smaller as you approach the core. G equals G m1 m2 over r squared. This is because the majority of the mass is usually below your feet, but as you get farther down, some of the mass is above you, changing gravity constantly, and the radius continuously gets smaller, making gravity weaker. As you reach the center, the mass on all sides of you are equal, canceling out gravity, making you free float. But when falling through the Earth, the acceleration may decrease, but your velocity is still large, making you zoom past the center. Halfway to the center, your speed is 1,500 miles per hour, which is 21 minutes after jumping in, and another 21 minutes before you get out. That makes it 42 minutes to travel through the tunnel through the Earth.
If there were a tunnel through the Earth, the density of air would be less and less as you approach the core. Since gravity acts on air, which actually has weight, there is less gravity at the core, and there would be less air particles. This basically means there would be less drag or air friction as you were falling through the center of the Earth. And this also means that terminal velocity would be at a higher speed, and also that parachutes would not work. You'd also create a sonic boom by breaking the sound barrier at the velocity of 15,000 miles per hour. But there wouldn't be much of a sound, unfortunately, because the sound waves need a medium to travel through. This is exactly like the jump from space, where there is also less air particles.
You have learned from Mr. Hall that momentum equals mass times velocity, but to really understand it, we must look at Einstein's famous equation, E equals mc squared. But this isn't the full story. This equation only describes objects that aren't moving. The full equation is E squared equals mc squared squared plus pc squared, with p being momentum. This may seem confusing, but it can be drawn as a right triangle with E as the hypotenuse and mc squared and pc as the legs, and use Pythagorean theorem, a squared plus b squared equals c squared. And with no momentum, we get back to E equals mc squared. But if the particle in question is massless, like light, then E equals pc. The closer the E is to pc, then the more it behaves like light. The object's velocity is equal to c times the ratio of the object's momentum to energy. If the momentum increases, pc gets closer and closer to equaling the energy, so the ratio gets closer and closer to being 1. And your speed gets closer and closer to light speed. But because of that tiny little bit of mass, the momentum side of the triangle will always be a little bit smaller than the energy side. No matter how hard you try to increase your momentum, it can never quite get to the point where P times C equals your energy, and thus your velocity can never quite reach the speed of light, all because the hypotenuse of the right triangle is a little bit longer than the legs. P equals mv is no longer accurate for particles moving as fast as the speed of light, so P actually equals mv divided by 1 square root of 1 minus v squared over c squared. But the square root part doesn't matter if your velocity is small compared to the speed of light, because when vc is really small and 1 minus something really small is basically just 1. So momentum p is approximately mv divided by 1, which is mv, which is why we say p equals mv. This momentum helps when we're learning about what happens when falling through the shaft while the Earth is spinning, and thus angular motion is mass times spin velocity times radius. This is an example of the Coriolis effect, which is why a ball curves weirdly when you toss it while riding a merry-go-round, and why hurricanes always spin counterclockwise in the northern hemisphere. When at the equator, you travel 1,670 kilometers per hour, but as you go to the Earth and sides, the Earth around you is still spinning once per day. But they don't have as far to travel, so they're going a lot slower. So if you jumped in the shaft, you'd be traveling east faster than the rock around you. So that after falling only a few kilometers, you'd crash into the eastern wall. The deepest hole ever drilled was the Kola Super Deep Borehole, which is 12,262 meters deep.
When standing at the edge of the hole to the center of the Earth, you gain potential energy. This is because you are 6,350 kilometers from the center and 12,700 kilometers from the other side. Since PE equals mass times gravity times height, it's easily calculatable. Kinetic energy is a different story. Kinetic energy equals 1/2 times mass times velocity squared. But the velocity is always changing as you jump through the hole, due to the weaker gravity. I mentioned it took 42 minutes to fall from the North Pole to the South, but you're probably wondering how I got that. This is the Earth. Now imagine an arbitrary sphere that is concentric with the Earth and its radius is from the center of the Earth and where the falling object is located. Since the object is constantly falling, the radius is constantly changing, and the mass is also. So we need to find the gravitational force inside the Earth because it's not the same on the outside. We calculate the force, which equals the gravitational constant multiplied by the mass of the Earth in the arbitrary sphere divided by the radius squared. The problem is we have the mass of the arbitrary sphere and the radius of it in the same equation. They're both unknown and changing. We can write the mass of the arbitrary sphere in terms of its radius. Imagine there is an object and it has some density, and imagine another object and it has the same density and twice the mass. And we can show that the volume of the second object has to be twice the volume of the first object, so this means that objects of constant uniform density, mass, and volume are directly proportional. They have a linear relationship. If you double the mass, you have to double the volume, and if you triple the mass, you have to triple the volume. Next, we need to know the volume of a sphere, where r is the radius of it. Now you can do the mass of the Earth over the mass of the arbitrary sphere and set it equal to the volume of the Earth over the volume of the sphere. We are assuming the Earth has a constant uniform density. The 4/3 pi cancel and solve for the mass of the arbitrary sphere, and that equals the mass of the Earth times the radius cubed of the arbitrary sphere over the radius of the Earth cubed. And if you plug that into the equation of Newton's law of gravity, and then you simplify that, then you can move the universal constant, or big G, and the mass inside the parentheses, and move r squared into the denominator, then cancel r cubed with r squared in the numerator, and then you get this. Next, we are going to use the simple harmonic motion, so the force equals k times x, where k is a constant called the spring constant, and x is the distance away from the equilibrium position. Set k to the following and set x to r, or the radius. Now the fact that we have this result, that the gravitational force inside the Earth is in a smaller form as the force in simple harmonic motion, shows that if you drop an object into the hole that is through the center of the Earth, it will move from opposite poles over and over. And in simple harmonic motion, the period is 2 pi times the square root of m over the spring constant, and the period is from north to south to north, so we're going to have to divide it by 2 later. And we can simplify this by the gravitational acceleration by the surface of the Earth, and we can cancel out all of the masses, so A equals G m over the Earth's radius squared. And the reason why this is useful is because you can find G inside of K. You can find gravitational acceleration in the spring constant, and so you can simplify further. So you have k equal the gravitational acceleration near the surface of the Earth times the mass of the object over the radius. Now we can put this all together and Solve for the period. Plug in k, move the radius to the top of the fraction, and then cancel out the m's at the top and bottom of the fraction. This shows that no matter the mass of the object, it'll drop at the same time. And so the only two numerical values are the radius and g. And the radius of the Earth is 6,365,800 meters, and divide by 9.8, and so the period is approximately 5,060.4 seconds. And remember to divide by 2, and you get 2,530.2 seconds, which is 40.17 minutes.